In this lesson, we're going to finish our conversation about determinants, and then we'll move on to some other topics as well. And so we're going to pick up where we left off last time. In the last lesson, we finished by saying that for any matrices bigger than 3 by 3, our other method of working along a row or a column just is not very effective or efficient. So we would like to know if we can do row operations so that we can then create a simpler matrix to work with. So the answer is yes, but certain row operations do have an effect on the result of the determinant, do actually change the determinant as you perform certain operations. So let's go through the different operations and see which ones really how the different row operations would affect the determinant. So let's start with these two. So the one on the left here, if I find the determinant, multiply the main diagonal, minus multiply the other diagonal, I get -10. And for the second one here, multiply the main diagonal, minus multiply the other diagonal, and I get 10. Now let's ask the question, how do these two matrices, or how do I take the left matrix and change it to turn into the right matrix? And what I want to point out here is we're swapping row 1 and row 2. So notice that when you switch the two rows, the result is you change the sign of the determinant. -10 becomes +10. So if two rows are interchanged, the determinant changes signs. Great. Right, let's try this one. Oops. Okay, so again, let's do the one on the left here. So multiply the main diagonal minus multiplying the other diagonal. It's the same one, so I still get -10. If I multiply, do the one on the right here, multiply the main minus the other one, I get -5. Now, once again, let's see what changed. As I go from the left to the right, notice that row 2 becomes half of row 2. We divide it by 2. And so notice that if I divide a row by 2, the result was that I divided the determinant by 2. So if a row is multiplied by a scalar, in this case the scalar was 1/2, then the determinant is also multiplied by that scalar. Okay, now factor out of row. One way to think about it is, I just want to explain one way to think about this. If I were to take that 1, 2, 2, -6, I'm going to notice at the bottom row, I can factor out a 2. So if I pull out that 2, I'm going to be left with 1, 2, 1, -3. The one on the left here, we got a determinant of -10. And so notice we can think of that as 2 times the other determinant, which was -5. So the point here is if we can pull out if we can factor out a number from a row, great, factor it out, and then whatever you pulled out, don't forget to multiply that by the determinant of the smaller matrix. So that's one way to think about it. Okay, not smaller, but the one with the smaller numbers in it. So that's one way to think about it. Let's try this problem. Okay, I get the one on the left. We've already done this a couple times. It's the same one. It's -10. And if I do the one on the right here, multiply the main diagonal minus the other one, we get, again, -10. This time the determinant did not change. Now, again, what row operation did we perform? Well, row 2 got replaced with, let's see, it looks like it was -2 row 1 plus row 2. Multiply the top row by -2 and then add to the bottom row. So what we're finding here is if a row is replaced by its sum with a multiple of another row, the determinant does not change. Now, this is a little bit nitpicky here, so let's be careful, because I know when we do row operations, sometimes I'll do a couple of steps at once. So please note that the determinant does not change as long as row 2 gets turned into itself plus doing something to a different row. So as long as you don't change row 2, you can add it to any multiple of any other row. But please note that if I also did something in row 2, maybe we had to subtract row 2, or maybe we had to multiply row 2 by a number, then the determinant will change, and you have to keep track of that. So the only way we can do this replacement without changing the determinant is if the row itself is not the row that's getting replaced is not changed. It's just added to another row, but the other row might be changed. Okay, so one more thing that we want to look at here. Let's look at these two. Once again, multiply the main minus the other one. So in this case, I'm getting negative 12. And if I do the other one here, multiply the main minus the other one, I get again negative 12. Now, what's changing here? Okay, this is not one of our row operations. I'll tell you that right now. There's no row operations going on. What I want you to notice is that this row turns into this column. And then likewise, the second row becomes the second column. What's changing is we're finding the transpose. And so notice that when we find the transpose of a matrix, the determinant does not change. So the determinant of A transpose is the same as the determinant of A. So keeping all these different properties in mind, notice that we can now, if I give you a matrix, so these properties also work. Okay, so quick side comment, these also work with column operations. We've only worked with row operations, combining rows, but please note there are such things as column operations, right? Multiplying a column by a constant or whatever. We haven't done any of that. It's not part of this course, but it theoretically exists. And so these same properties would apply. We can make determinants easier to evaluate by using row operations. So again, 3 by 3 matrix is not a big deal. We can find the determinant the way we learned last time. But 4 by 4, already that becomes a giant pain in the neck. So notice that now we are able to do these row operations. The only thing we have to be careful about is, do we change the determinant by doing operations? So let's find this. Let's find this determinant. So we're finding the determinant of negative 2, 2, 3, 1, negative 1, 0, 0, 1, 4. Now, please remember, and we saw this at the end of the last lesson, all we need is a triangular matrix. In other words, all we need is echelon form. We don't need reduced echelon form. So our goal is just to get that echelon form, which means, remember, echelon form, the pivots don't have to be 1. They can be any number. So I'll tell you right now, I can leave that negative 2 right where it is. It's actually not going to cause us any problems. So I'm going to go ahead and do that. I'm going to leave the negative 2 where it is. So we get negative 2, 2. You know what? I take it back. Come on. Yeah, leave it. Why not? Okay, so we're going to leave the top one the way it is, leave the bottom one the way it is. And now I need to just change the middle row, row 2. Well, notice that to do that, what am I going to do? Row 2 is going to become, now, it is really tempting. I'm going to write something, but then I'll erase it. It is really tempting to say, take row 1 plus 2 row 2. Okay, it's really tempting to do that because that's kind of the way we would normally do this. But notice that if I did that, the determinant will change. The determinant stays the same when we do replacement. The determinant stays the same only if the row being replaced is not altered in any way, but the row you're combining with is. So for that reason, I don't think that this is a good option, because again, the determinant is going to change. Come on. So I'm going to do something a little different. Again, if I want to do an operation that does not affect the determinant, I'm going to replace row 2 with row 2 plus, I'm going to do 1/2 of row 1. Notice by making that change, row 2 is not changing. It's just being added to a different row that is being changed. Now, the annoying part is fractions, and we'll deal with that, but just kind of keep in mind that we're doing this so that we can avoid actually changing the determinant. So if I multiply the top row by 1/2 and add the bottom row or the second row, I get 0. And the next one, I get another 0, and then I get 3/2. Okay. Great. Again, my goal here is let's put this into echelon form. And notice that to put this in echelon form, the only thing I have left is to swap the second and third rows. I'm just going to switch them. And now the only thing I have to be careful about is if I switch two rows, the determinant changes signs. We just need to be careful about that. So we have an extra negative there. And so my answer is going to be negative times. Now again, now that it's in diagonal, it's in echelon form, my determinant is just going to be the product of those numbers along that diagonal. So it'll be times -2 times 1 times 3/2. So then my final answer here is 3. So the determinant of this matrix is 3. Now again, it's a 3 by 3 matrix. We could have done this using the other method. That's great. Nothing wrong with that. But again, when you get into bigger matrices, we'll do a 4 by 4 in a second. You really don't want to do that. Okay, so definitely know how to use row operations to simplify the determinant work. Okay, let's try this example. Again, it's a 4 by 4. Let's see here. Okay, so I'm going to start with my problem that we're doing here. So we got 2, -8, 6, 8. And then we get 3, -9, 5, 10, -3, 0, 1, -2, and 1, -4, 0, 6. Okay, the first thing I want to do is get a 1 in the upper left-hand corner. Now again, I don't actually need to do that, but if I'm going to work with this 4 by 4, there's going to be a bunch of operations. I kind of want that 1 to be there. Now, there are a couple ways I could do it, and different choices will still result in the same answer, though the work will look different. A lot of people might look at this and say, let's just swap the top and the bottom rows. That's cool. That's awesome. Switching the top and the bottom rows is perfect. Alternately, I'm going to notice that the top row, I can divide everything by 2 and not create fractions, right? I want to try to avoid fractions if I can help it. So I think that's what I'm going to do. I'm going to divide the top row by 2. Now again, one way to think about that is it's kind of like I'm factoring a 2 out of that whole row. So if I'm pulling out a 2, then that 2 is going to go out in the front of my determinant. I'm not making any other changes. Okay. So now my top row is good. Okay, for my second row, I'm going to multiply the top row by -3 and then add the second row. Notice that the second row is not changed. I'm replacing the second row with itself plus a multiple of another row. By doing that, we're not changing the determinant, which is great. So I'm going to multiply the top row by -3 and then add the second row. So I get 0, 3, -4, -2. Okay, multiply the top row by +3 and add the third row. We get 0, -12, 10, 10. Okay. And then now again, we need to be careful. I could do top minus bottom. I could do row 1 minus row 4. But notice that then I would be changing the sign of row 4, and we don't want that. We want it to be row 4 plus some multiple of row 1. So I'm going to do row 4 minus row 1, again being careful so that I don't change the determinant. So row 4 minus row 1 will give me 0, 0, -3, 2. Okay. Let's see here. So I'll leave that 2 there. 1, -4, 3, 4. Now, part of me is tempted, and I'm going to leave the second row also the way it is. Part of me is tempted to take the third row and divide by 2 just to get smaller numbers. But you know what? I'm going to leave it alone because notice that if I just take the third row and add it to 4 times the second row, right? Multiply the second row by 4 and then add the third row, I'm going to get a 0 right where I want it. So I'm doing the second row times 4 plus the third row will be -6 and 2. And then the bottom row is 0, 0, -3, 2. Okay. Right, so my top row is good. Second row is good. My third row, now again, I could look at the third row and say, hey, let's divide by 2. You know what? I'm not going to bother. I'm just going to leave it. Oh, I forgot the 2 out in front. I'm sorry. Let's not forget that. Okay. Okay. Now we have the bottom row. So one more time, I have to make sure that when I combine the bottom row with something, I don't change the bottom row. So what I'm going to do is I'm going to multiply the third row by -1/2. So that the third row is being changed, but then I'm combining it with the fourth row and then replacing the fourth row. Again, my goal here is let's not change the determinant. So again, I'm multiplying the third row by -1/2 and then adding the bottom row. So I get 0, 0, 0, and then -1/2. This will give me 1. Once again, there were lots of choices I could have made. I'm just trying to avoid choices that will change the determinant. I want to be careful about this. Finally, my determinants is going to be that 2 times the product of these diagonal positions. And so I get a final answer here of, looks like -36. There we go. So the term is -36. And that was a whole heck of a lot easier than taking this 4 by 4 matrix and breaking it down into a bunch of 3 by 3 matrices. Okay. So let's consider what happens if I take this matrix that we just worked with, and I'm going to make one small change. I guess I made a couple small changes. Whoops. Come on. Okay, so the only thing that changed was that the bottom, a couple of entries there changed. So I'm going to go ahead and just tell you rather than going through all those row operations again, I'm just going to tell you that that determinant that we're calculating, it's going to end up turning into, it's going to reduce down to this. Okay, so there's that 2, it's fine. Yeah, 1, -4, 3, 4. I don't even remember what it was anymore. Let's see. 3, nope, that was a 0. 3, -4, -2, 0, 0. I forgot already. -6, 2. And then here's what the bottom row is going to turn into. The bottom row is going to be 0, 0, 0, 0. Okay, that's a 0 here. Okay. So notice that if I then finish calculating this determinant, it'll be 2 times 1 times 3 times -6 times 0. Notice my determinant is going to be 0. Now let's think about that for a second. We got a determinant of 0. Great, perfect, fantastic. But what else do we know about this matrix? Notice that when we took this square matrix, because of course we can only find the determinant of a square matrix, notice when we found the determinant of the square matrix, we got 0. But when we reduced the square matrix, notice that we found that we did not have a pivot in every row and every column. Whereas on this example, Whereas on this example, we had a pivot in every column and we got an answer that was non-zero. Think about what we talked about a couple classes ago. We had a lot to say about matrices where there was a pivot in every column. In fact, we had a whole theorem about it. It was called the invertible matrix theorem. We said that a matrix is invertible if and only if there's a pivot in every row and every column. Okay, and then there was a bunch of stuff attached to that. But notice that now we have one more thing to add to that. Notice that a square matrix is invertible and all of the stuff that goes along with that, if and only if the determinant is non-zero. This gives us one more condition to add to that invertible matrix theorem. If the determinant is non-zero, then all those other properties go along with it. And if the determinant is equal to zero, then the matrix is not invertible. Okay, so that's great. We're not going to add that to the invertible matrix theorem right now. We're going to do that. We're going to continue finding things to add to that theorem. So we will add this determinant stuff to that theorem in a later lesson. Okay, some more properties of determinants. Let's verify. Here's a property. Let's verify that the determinant of A times B is equal to the determinant of A times the determinant of B. Okay, we've got A and we've got B. The determinant of A is equal to, let's see, 12 times 3, which would be 36. Nope, let's try it again. 12 minus 3, which is 9. I can do this, I really can. Come on. Okay, so that's 9. And then the determinant of B is equal to, it's going to be 8 minus 3, which is 5. Okay, let's find A times B, right, using those matrix operations we did a couple of lessons ago. Okay, so let's see, row 1 times column 1 will be 24 plus 1 is 25. Row 2 times column, or row 1 times column 2, excuse me. So 6, 1 times 3, 2 is going to be 18 plus 2 is 20. Row 2 times column 1 is going to be 12 plus 2 is 14. And then row 2 times column 2 is 9 plus 4, which is 13. Those are big numbers. Okay. The determinant of AB, so the determinant of that result of the product, so it's going to be 25, 20, 14, and 13. So if I multiply these, I'm going to get, hold on, I can do this, 325, I think. Hold on. 250. Yeah, I'm pretty sure that's right. I'm going to find out in a second, aren't I? Minus multiplying the other way, 20 times 14 is 280. And if I subtract those, I'm going to get 45. Yes, I'm going to get 45. And it's worth observing that the determinant of AB is equal to the determinant of A times the determinant of B, because 45 is equal to 9 times 5. Okay, that's cool. So this is a useful property, right? If we have the determinant of a product, we could instead find the determinant of each part and then multiply the results. And notice that that's kind of nice because these two determinants were pretty easy to calculate. This one was kind of a pain in the neck, especially because first we had to find the product of the two matrices. And of course, if it was bigger than 2 by 2, it just becomes a lot more work. So and I really don't want to use the word distributive here, but basically it's sort of kind of, you know what, I'm not even going to say that word. Please note, this does not work if you're adding two matrices. So that if you add two matrices and find the determinant, the result is not the same as adding the two determinants together. So, don't take this too far. Now, here's a nice little shortcut. Find the determinant of b cubed. Now, I could multiply b times itself again, nothing wrong with that, and then find the determinant to the result. But notice that what I'm asking you to find, or what we're being asked to find, I guess I should say, is the same as the, wow, where'd I get a log? Definitely not logarithms. Determinant. There we go. This is the determinant of b times b times b. Well, think of that last property. This is the determinant of b times the determinant of b times the determinant of b. In other words, this is the determinant of b cubed. So I'm going to go ahead and find that determinant of b, which would be 8 minus 3, and then I'm going to cube that result. So my final answer is 125. And so, by the way, you really don't need to write any of this stuff, right? This is just me explaining why I'm doing what I'm doing. But basically, the determinant of b cubed is the same as the determinant of b, and then cube the result. And certainly for a 2 by 2 matrix, that's a whole lot easier to do. Okay, so let's evaluate the determinant of this product one more time. If I didn't think about this clearly, I would multiply the two matrices, which is a whole lot of work, and then you're going to find the determinant, and it's going to be a whole lot of work. So I'm going to split this up as the determinant of the first one times the determinant of the second one. The first one here, I'm going to notice that it's already in diagonal. It's already diagonal, which is great. So this determinant is going to be 7 times 5 times 1 times -1. Fine. The second matrix is not in echelon form. That's okay. We could put it into echelon form, but it would require a bit of work here. I'm going to think about this problem like we did last lesson, because I'm going to notice that this row has almost all zeros. In fact, if I were to work along that, I'm sorry, not row. If I were to work along that column, actually, I guess I could have done the top row too, couldn't I? You know, let me do that just because it's a little easier to visualize. Let's erase that. Come on, there we go. Okay, yeah, let's work along the top row. I guess that makes a little more sense. So if I work along the top row, I notice that my determinant is going to be 4 times this smaller matrix. And then that smaller matrix, the determinant is going to be 3. If I work along the top row of that one, it's going to be 3 times this smaller matrix. And the determinant of that smaller matrix is 2 minus 6. So I am left with -35 times, looks like 12 times -4 is -48. I'm not going to bother doing this, although I will say it's negative, or positive, I should say. I don't know. It's a number. You get the point. It's a big number. But yeah, so notice that for some matrices, if it's in echelon form, awesome. You know the determinant. If there's a bunch of zeros, maybe you want to consider using that method, right? What we did last class. Or if there aren't a bunch of zeros, now we know that row operations can help us get to the answer as well. Okay, so this is how we're going to tackle finding determinants for matrices of various sizes. Now let's talk about a couple of ways that determinants can be used. And we're going to start with one that I'm going to tell you right now is not all that useful, but I'm going to share it with you anyway. Just some people might like it. It is possible to solve a system of equations by finding a bunch of determinants. Okay, and here's what I mean by that. This is called Cramer's rule. So consider the problem of solving this matrix equation Ax equals b. And we're going to define A sub 1 of b to be the matrix where we take matrix A and we replace its first column with B, right? We replace it with the stuff on the right side. Well, it turns out that the solution for x1 is just the determinant of that new matrix divided by the determinant of A. And then we can do that again, find x2, all right? Find A sub 2 of B. and determinant of that divided by the determinant of a. So we can use this process to solve for x1 and x2. I will tell you right now, whoops. Well, I'll tell you right now, we're going to do this example. Come on, what is happening? We're going to do this example right now, but I'll tell you right now, it's probably going to be quicker to do row reduction. So I wouldn't worry too much about Cramer's rule. Although if you like it, great, go for it. I'm not going to, at no point am I ever going to say you have to use Cramer's rule to solve a problem. If I gave you this problem, my assumption is you're going to change it into augmented matrix, you're going to use echelon form and so on. But this could be done with Cramer's rule. So let's just see what it looks like. See if anybody likes it. So matrix A is going to be the coefficient matrix. So 4, -2, 3, -5. And vector B is the stuff on the right side. So that would be 10, 11. So A sub 1 of B is where we replace the first column of A with B. 10, 11, and then this is still -5 or -2, -5. So if I find the determinant of A sub 1 of B, that would be -55 minus -20, which is -35. Okay. We're going to also find A sub 2 of B. So now we're going to take matrix A and replace the second column with B, which was 10 and 11. The determinant of that matrix would be 44 minus 30, which is 14. Great. And I also need the determinant of A. So let's see, A was 4, -2, 3, -5. So this is going to be -20 minus -6, which is -14. Okay. Okay. So it turns out that x1 is going to be the determinant of A sub 1 of B divided by the determinant of A. So that would be -35 over -14, which reduces to 5/2. And then x2 is equal to the determinant of A2 of B divided by the determinant of A, which would be 14 over -14, which is -1. So this is a great answer. If you really feel like writing in vector form, the vector form would be 5/2, -1. Okay, fine. This is what Cramer's rule look like. Again, I don't think that this is all that useful, but great. Okay, if you like it, go for it. Another use of the determinant, which I'll be honest is not a very good way of using it. I'm being very skeptical about the determinant. We're going to see it again later, in later chapters where it's a lot more useful. But another way to use the determinant is this. Let A be an n by n matrix, and C sub ij is the cofactor for entry A sub ij. We already talked about that. So one way to find A inverse is going to be 1 over the determinant of A times C transpose. C transpose is basically matrix C is going to be the matrix where every entry of that matrix is going to be the cofactor. So C11, C12, C13, and so on. You're going to create this whole matrix of cofactors, and then this is now the transpose of that. C transpose is called the adjugate or the classical adjoint of A and can be denoted adj A. Not really sure if adj is short for adjugate or adjoint. Doesn't really matter. I will tell you right, I can't think of a single time in the rest of this course where I ever use those two phrases, so you don't really need to know that for this course. But if it comes up in future courses, now you know what it means to be the adjugate or the classical adjoint. Not easy words to say. As I said a minute ago, generally it's quicker to use the other method to find A inverse, right? Couple classes ago, couple lessons ago, we said that we can find use row operations with the augmented matrix to find A inverse. That's typically going to be easier, less labor intensive. But let's just see one quick example here where we're using this method to find an A inverse. So here's A, find A inverse. So let's find a bunch of the C's here. So C11 is going to be -1 to the 1 plus 1 power times the smaller matrix where we remove row 1 and column 1. And I'm going to get 1 as that value. I'm going to create a grid here to organize my work. Okay, C12 is going to be -1 to the 1 plus 2 power times the smaller matrix, remove row 1, remove column 2. I'm going to get the determinant of that is -2 minus 3, so -5, but the negative out in front makes that a +5. C13 is going to be -1 to the 1 plus 3 power times the smaller matrix, -2, 1, 3, 0, and I'm getting -3. Okay, I'm just going to do the rest of these here real quick. I could probably pause the recording and just show you the final answers, but you know what? I'm not going to. And so I'm getting, oh, that's 2 plus 2. So I'm getting 2 for that. And C sub 2, 3 is -1 to the 2 plus 3. Six. This is very riveting video, I know. Especially since I'm probably making mistakes, but that's okay. You get the point. Of course, I could probably just make up numbers and you'd still get the point, but you know what? I'm not gonna. Okay, so I'm getting 2 minus -4 is 6. Okay, so these 9 entries make up the 9 entries of C. Oh, you know what? Let me also find the determinant of A. I'll work along the top row, so it'll be 2 times -1 to the 1 plus 1 times 1101 plus 2 times -1 to the 1 plus 2 times its smaller matrix plus 0 times who cares. So I'm getting 2 times 1 minus 2 times -5, which gives me 12. Okay, so finally, A inverse is going to be 1 over that determinant of A, so 1/12, times C transpose. Now again, those 9 entries that I created are C, so the first row of C becomes the first column of C transpose. Second row becomes the second column. Third row becomes the third column. And there's my inverse. Once again, you're better off just doing the other method. Although I will point out, if I brought that 1/12 inside, every single entry is going to be a fraction. So probably the work to do the row reductions is not going to be very much fun. But you know what? It's all right. Okay, so far I've shown you 2 applications of derivatives, and both times I said don't bother. Okay, because there's better ways that we've already learned. Let me share with you a couple of other ones that are not as well, that are more useful, I guess I should say, that are more useful. Come on. If A is a 2 by 2 matrix, then the area of the parallelogram determined by the columns of A is the absolute value of the determinant of A. Before we talk about the second part there, let me just draw you a picture here. So let's say that A is made up of a couple of vectors, so v1 and v2 are the columns. And if I draw a picture here, here's v1. And by the way, I'm going to assume that they're not parallel vectors. So here's v2. So the parallelogram would be repeating v2 up here, repeating v1 up here. And so the area of this parallelogram is the determinant of A. Now for the 3x3 matrix, the volume of the parallelepiped. Okay, right away, that's an awesome word to say. I encourage everyone to pause the video and say the word parallelepiped because it is so much fun. Go ahead right now. Okay, good job. Parallelepiped. The volume of the parallelepiped determined by the columns of A. A parallelepiped, and I'm going to try to draw it and I'm going to fail badly. But here's one vector, here's another vector, here's a third vector. The parallelepiped is basically keep extending them all. And you create sort of a, now this is not intended to look like a cube or a rectangular prism. Each one of these is supposed to be slanted. There are not supposed to be any right angles, or at least there don't have to be, is my point. So the way I describe it is kind of like a slanty box or maybe a stick of butter that's been set out in the sun for too long. So it's starting to sag a little bit. This is what I mean by parallelepiped. But again, if you think about here's V1, here's V2, and then here's V3, and then you just keep repeating those vectors to create the sides of this box. That's what we call a parallelepiped. That actually came out fairly decently, I don't mind telling you. I'm kind of excited about that. Okay, so a couple examples. Let's find the area of the parallelogram with these four vertices. So let me graph this. We have the point -2, -2. We have the point 0, 3. We have the point 4, -1. And we have the point 6, 4. Up, there it is. Okay, so here's our parallelogram. We could verify that it's that is a parallelogram, but we don't. I'm going to take the problem's word for it. So this vector right here, notice that to go from one to the other, basically we have to go over 2 units horizontally and up 5 units. So that would be the vector 2, 5. And this vector here, we have to go over 1, 2, 3, 4, 5, 6. We have to go over 6 and up 1. So that would be the vector 6, 1. Yep. So the area that I'm looking for is going to be the determinant of the matrix where one column is 2, 5 and the other column is 6, 1. Actually, let me make one small change, and you'll see why I'm doing this in a second. I'm just going to erase that letter A there for a second. Okay, so let's find the determinant of this matrix. So this determinant is going to be 2 minus 30, which is -28. And of course, this is a problem because we can't have an area that's a negative number. That's just silly. So the area that we're looking for is going to be the absolute value of that determinant, which is +28. There's always the possibility of getting a negative number for a determinant. So when we use determinant to calculate area or volume, we just take the absolute value of that answer. Okay, let's try this one. Find the volume of the parallelepiped with one vertex at the origin and adjacent vertices at these 3 points. Well, please notice that if the origin is one of the vertices, then the other endpoint dictates the vector. That I don't think that made any sense at all. Let me try again. If we have a vector that starts at 0 at the origin and ends at this point, that is going to be the vector 1, 3, 0. So that's my first column. Yeah, the second column is going to be the other terminal point, -2, 0, 2. And the other terminal point will give me my third column, so -1, 3, -1. Okay. Um, we can find this determinant using any method that we've learned, right? We can use row operations. We can pick a row or column, right? 3 by 3 are not too terrible, especially because there are those zeros. Why don't we just use the first column, right? It's not too bad. So it's going to be 1 times -1 to the 1 plus 1 times its smaller matrix, plus 3 times -1 to the 2 plus 1 times its smaller matrix, plus 0 times who cares because it's a 0. And so I'm getting 1 times 0 minus 6, minus 3 times 4 minus, nope, let's try it again. Come on. It's 2 minus -2. So I'm getting -6 minus 12 is -18. So the volume that I'm looking for is going to be positive 18. Cool. Again, absolute value. And by the way, there's no reason I had to put the vertices in that order. I could have put, I'm sorry, that I had to put let me try that one more time. There is no reason that I could not have put, let's try again. There's no reason that I put the vectors, the columns in that order. I could have put the columns in any order that I want. Please notice that switching the order of those columns would do nothing more than change the sign of the determinant. But if we're going to take the absolute value, who cares? Change the sign as much as you want. Also, I took these vectors and made them the columns. I could have taken that vector 1, 3, 0 and made it the row, the first row, or the whatever. Notice that by doing that, I'm doing the transpose of the matrix that I chose to work with. But again, transpose does not change the determinant. And so the result would still be correct. So lots of choices available to us. Okay, so that closes the conversation we're going to have here about determinants. Now we're going to start a brand new conversation. We're going to start a brand new chapter. And this chapter is all about what are called vector spaces. So let's start well, we're going to define vector spaces in just a little bit, but I want to point out that we have already been working with vector spaces. So we're going to be working with some abstract sets called vector spaces. And I say abstract because so far we've been working with some really concrete vector spaces. We've been working in R2, R3, really R anything, but for the most part R2 and R3 where we can visualize what's going on. So far, that is what we've been working with. When we said vector, we meant the vector 1, 3, -1, or 1, 3, 0 was the last example. Doesn't matter. The point is, when we talked about vectors, we talked about a vector in R2 or R3, where it was a vector with 2 components, or a vector with 3 components, or whatever. Okay. But the idea of a vector is more than just a thing with 2 components or 3 components. The concept of a vector is much more than that. So those were very concrete examples of vectors. But now we're going to start talking about some more abstract vectors. But the thing that we want to understand is that everything we've learned about R2 and R3 will still apply to these more abstract sets. And that's going to be the conversation that's going to take us, over the next several lessons, talking about these vector spaces and how to work with them. So on the next slide, I'm going to give you a bunch of properties of vector spaces. There were so many I didn't have space to write this. So I'm just going to tell you right now that on the next slide, when you see u, v, and w, these are vectors in a vector space V. Again, you can visualize u, v, and w as just having, 2 components, 3 components, but understand that they could also be more abstract. And we'll see lots of examples of vector spaces before we're done today. And then when you see these italic letters C and D, that refers to real numbers, any real number, okay? Could be C and D. Okay, so so a vector space contains objects, which we call vectors. And on these vectors, we're going to define two operations. We're going to define what it means to add two vectors, and we're going to define scalar multiplication. And a vector space is subject to these 10 axioms or rules. Okay. So the first rule is it has to be closed under addition. Now again, a vector space is made up of a bunch of objects, okay, a bunch of elements, which we call vectors. In order to be a vector space, it needs to be closed under addition. What that means is if you were to take any two elements of this vector space and add them together, the result needs to be another element in that vector space. We're going to see lots of I don't know about lots, but we'll see a bunch of examples today. So we can some where this property works and some where this property doesn't. But this is the first property. If you take any two numbers in this, any two elements of this vector space and add them together, you need to get a result that is still in the vector space. It needs to be closed under scalar multiplication. Again, if you take any element in this vector space and multiply it by any real number, the result still has to be an element of the vector space. So that's what it means by closed. It means you do something, but you don't leave the vector space. The result stays in the vector space. Addition is commutative. Okay, so we have to be able to switch the order that we add things and still get the same result. Addition has to be associative. We can change the order in which we perform addition and still get the same result. The zero vector. So the zero vector has to be an element of a vector space. Okay. And again, we're defining the zero vector. Again, it doesn't have to be the number zero, but we're defining the zero vector as just any vector that when you add it to another vector, the result is that same vector. Basically, the zero vector is one that you can add to another vector without actually changing it. Opposite vector, okay? There has to be some vector that will, sorry, if I give you any vector u in the vector space, its opposite also has to be in the vector space. And opposite meaning when you add those two together, the result is that zero vector. Okay, so there has to be an opposite. And again, we're used to the opposite being, hey, just take u and multiply it by -1. All right, that's probably going to be generally true, but we're going more abstract, so that's not necessarily the case. The distributive property, if we distributed a scalar multiple to the sum of two vectors, the result has to be what we expect. Likewise, if we have the sum of two real numbers, we can multiplying a vector, we can distribute the vector. Those two are pretty much universal. They're going to work, but we want to state it. The scalar multiplication is associative. Again, you can switch the order. You can either multiply the scalars one by one or multiply them first and then multiply by u. Again, this one's fairly going to be true generally. And then scalar multiplication by 1. Okay, if you multiply a vector by 1, the result should be the original vector again. Okay, these are all the properties. For the most part, we're going to be interested in these 6. Again, those last 4 are not that. They're generally going to be true, and we don't really need to stress over them. And in fact, even these 2 are not going to be huge. Really, it's mostly about, is it closed under addition? Is it closed under scalar multiplication? Is the zero vector in there? And does a vector have an opposite? Basically, if I ask you verify this is a vector space, these are really the 4 that you want to put in the effort to check, because all the rest of them are I'm not really too worried about that. As we go through, I might make some comments about that, but in general, I'm not too worried about them. Okay, so let's play with some vector spaces, or let's in some cases, let's see if they are. So let's let S be the space of all doubly infinite sequences of real numbers. So a sequence of real numbers starts at some place and goes on forever. Doubly infinite means it goes forever in both directions. There's no beginning and there's no end. We want to show that this is a vector space. So let's verify those 4 properties. Okay. First of all, adding. So let's consider xk and yk. Okay, and let's see what it means to add those together. So xk would be dot, 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 x negative 2, x negative 1, x0, x1, x2, dot, dot, dot. We're going to add that to yk, which would be y negative 2, y negative 1, y0, y1, y2, dot, dot, dot. So if I add these together, I'm going to define the addition as basically just add the corresponding pieces. So it'll be x negative 2 plus y negative 2, x negative 1 plus y negative 1, x0 plus y0, x1 plus y1, x2 plus y2, dot, dot, dot. Again, the question we're asking is, when I add these together, do I still get an element of that same set? And the answer is yes. This is an element of that vector space. That's a terrible boldface S, but it'll do. So when I add those together, I still get an element in S. So this works. Likewise, if I did a constant times yk, I could define that as just cy negative 2, cy negative 1, cy0, cy1, cy2. And this is also an element of this set. That's a better boldface S. So multiplying by a scalar still stays in the set. The zero vector does exist. And in fact, it's just the vector 0. It's just the doubly infinite sequence where it's just all zeros. Certainly that is a doubly infinite sequence, so that is in S. So the zero vector does exist in our set. And then finally, the opposite of yk is going to be basically just take the opposite of each entry. So dot, 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 negative y negative 2, negative y negative 1, negative y0, negative y1, negative y2. Okay, so there's our opposite, because certainly if I take that and I added it to my yk, the result is going to give me all zeros. So that's the opposite. Okay, so again, I could verify the other 6, but really these are the 4 that concern me. Because if I define addition in this way, distributive property is going to, definitely going to follow associative property, commutative, all that is going to follow just because we know what addition means. Okay, let's try another one here. Let's define Pn as the space of all polynomials of degree at most, n. So Pn means all the polynomials that have degree of n or smaller. And let's show that this is a vector space. Okay, well, once again, let's see what happens if I take P of t plus Q of t. And by the way, I'm going to define Q of t as b0 plus b1x, or t plus, you get the point, up through bn t to the n. Okay, just so I have a different letter. So if I add these together, I'm going to combine corresponding parts. So it'll be a naught plus b naught. And then the t's will be a1 plus b1 times t. And then a2 plus b2 times t. And then the last term will be an plus bn times t to the n. And that is certainly an element of Pn. Okay, so that works. So this is closed under addition. Now, I want to point out something that we should really consider here for a second. An and bn could be anything. What if these happen to be opposites? In other words, what if when I added these polynomials together, that coefficient on t sub n ended up being 0? We always need to be on the lookout for exceptions, for loopholes. What if that happened to be a 0? Well, notice that if that were the case, now this sum is not an nth degree polynomial. It's an n minus 1 degree polynomial. The degree went down. But notice that that's okay. Because the degree is at most n. So even if some of those coefficients are zeros, even if a bunch of the coefficients are zeros, the result might not be a polynomial of degree n, but it will definitely be a polynomial of at most degree n. So we're good. Okay, so we're still in Pn, so be careful. We'll see an example in a minute where that actually is not the case, but for right now it works. Multiplying by constant, I could do just CA naught times t, and then CA1 times t. Oh, I'm sorry, the first one does not have a t on it. Plus CA2t squared. Oh, I forgot the squared on there, I'm sorry. Plus dot 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 plus CAN times t to the n. And again, this is an entry. This is an element. That's not an R. Doggone it. It should be a P. This is an element of Pn. Okay, so again, we're left with a polynomial of degree at most n. So that's still in Pn. Great. The zero vector is in there. The zero vector is just going to be 0 plus 0t plus 0t squared plus dot 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 plus 0tn. Now, again, we want to be careful. This is not a polynomial of degree n. This is a polynomial of degree 0. But that's okay, because polynomials of degree 0 are still in this set. So it is closed. And then certainly the opposite of p will just be negative a naught t plus negative a1t minus a2t squared plus dot dot dots minus an t to the n. Again, the opposite is in Pn. All four of those properties hold. And so therefore this is a vector space. Great. Now, again, let's look at an example that is not a vector space. Now I'm defining this new one, pi sub n, as the space of polynomials of degree exactly n. Okay, so notice that all of my polynomials is exactly the same, but now we're removing the possibility that that lead, or that biggest, the coefficient on t to the n, we're removing the possibility that that coefficient is 0. We want to show that this is not a vector space. Well, if you're showing something is not a vector space, all you need to do is make one of those axioms fail and you're good. Okay, so let's, and there's a bunch of them that could work. It is not closed under addition. Okay, if I did P of t plus Q of t, it would be same one we did before, A naught plus B naught, and then A1 plus B1 times t, and then A2 plus B2 t squared. And then an plus bn times t to the n. Well, again, there is a possibility that this could equal 0. Okay, I'm going to put a question mark. Not always, but there's a possibility, right? An could be anything, bn could be anything. So this is not an element of pi n, right? Because if that coefficient was 0, now the polynomial is no longer n. Likewise, zero vector, which would have to be 0 plus 0t plus 0t squared dot 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 plus 0t to the n. This is not an element of pi n. Okay, so once again, this zero polynomial is degree 0. Well, pi n is just degree n. So for that reason, this is not a vector space because the 0 vector is not in there. So by the way, you did not have to do both of these. Just pick one. As soon as one of these fails, it is not a vector space. Okay, I just wanted to show you guys a couple different ways to show that. Let's take a look at another example of a vector space. Define F as the space of all real functions. Okay, so F is just every real valued function. We want to show that it is a vector space. Okay, let's play around with this a little bit. If I had f of x plus g of x, well, f is a function, g is a function. If I add them together, the result is still a function. So it's in that vector space. If I do a coefficient times f of x, that is certainly in the vector space. The zero vector is basically the zero function, and that is in the vector space. And the opposite of f is in the vector space. Okay, so all those axioms applied, and so we're good. Okay, so these are just a bunch of different examples. Now, how about this one? Let's define z squared as the space of vectors in R squared with integer elements. So we already know R squared is a vector space. We've been working with it since we started here, but I'm defining z squared as it's only integers. Okay, so a and b can only be positive whole numbers or negative whole numbers. We want to show that R squared is not a vector space. Well, if I were to add two vectors, if I were to add these a, b, c, d, these are all integers. If I add them together, well, a plus c is still going to be an integer. B plus d is still going to be an integer. So this is in z squared. So that one's not a problem. The zero vector would just be 0, 0. Well, 0 is an integer, so that's in there. In this example, actually, there's only one of our axioms that fails, and that's the coefficient. If I were to multiply by c, now this is really important. C has to be any real number. If c was an integer, then we would not have a problem. But if c was a fraction, if c was some kind of a decimal, c times a is not an integer. C times b is not an integer. And so for that reason, this scalar multiple is not an element of z squared. And so for that reason, this is not a vector space, right? Sometimes there's multiple, if something is not a vector space, sometimes there's multiple axioms that fail. In this case, it was really only that one. I'm pretty sure, unless there's something I'm missing, I'm pretty sure that all the other axioms do apply. Okay, so this is what we mean by a vector space. Now, let's talk about subspace. So a subset is just a smaller set within a larger set. It's kind of right there in the word there, subset. A subspace of a vector space is some subset of H that should not be there. So a subspace of a vector space V is a subset H of V. So H is going to be the subset. Now, in order to be a subset, let's try again. In order to be a subspace, there's only three axioms we need to worry about. Okay, because and here's the reason. All the other seven axioms are automatically going to be true because we are assuming V is a subspace. So all the different properties of addition and stuff will automatically work. But we want to verify, we need to make sure that H is itself a vector space, even though it's inside of a bigger vector space. So in order for H itself to be a vector space, we need to make sure that all these properties are closed within H itself. So for example, it needs to be closed under addition. If you have two vectors in H, we need to make sure, we already know that if you take two vectors of H and add them together, you're going to get a vector in V, right? Because V is closed and everything in H is also in V. But we need to make sure that H is closed. So if U and V are in H, adding them together still needs to keep us in H. It needs to be closed under scalar multiplication, right? So if you take any vector in U, its scalar multiple, any vector in H, its scalar multiple still has to be in H. And the last condition is the zero vector. Okay, we need to make sure that the zero vector, we know the zero vector is in V. We need to make sure it's also in H. Okay, so these are the only three we need to check if we're asked to prove that something is a subspace of something else. Every subspace of a vector is a vector space in its own right. Okay, so every subspace is itself a vector space. It just happens to be a smaller piece of an even bigger vector space. However, since it's a subset of an already established vector space, not all axioms need to be verified. So I just said that. A couple examples we've already experienced. P sub n is a subspace of F, right? F is all the functions. P sub n is all the functions that happen to be polynomials of degree at most n. So for that reason, P sub n is a subspace. It's also a subset, so it is a subspace of F. Z squared is not a subspace of R squared, right? Z squared is certainly a subset, right? Everything in Z squared is also in R squared, but Z squared is not a vector space. It failed that one property, so it is not a subspace. Okay. Now, sometimes students like to think that R squared is a subset of R cubed, and it's not. R squared, all the entries only have 2 entries. R cubed has 3 entries. They're not subsets. However, we could consider vectors in R cubed that look like the vectors in R squared. So if I consider H as if I consider all the vectors in R cubed where the third component is just a 0, I'm going to call that subset H. Okay, so this is A can be any real number, B can be any real number. It's just that the third component is 0. We want to show that H is a subspace. So again, 3 properties to show. We want to take 2 vectors in H, so A, B is 0, and then how about C, D and 0? If I add them together, I'm going to get A plus C, B plus D, and 0. Again, to be an H, the first 2 components can be any real number. The last component has to be a 0, and we got that. So there's H. Scalar multiples. Scalar multiple of A times B, scalar multiple of AB 0 is going to be CA, CB, and 0. Again, the first 2 entries can be any real number. The last one has to be a 0, so that's an H. And then the last one is that the 0 vector has to be there. Well, the 0 vector is made up of all zeros. Again, the first 2 entries can be any real number, even 0. The last entry has to be a 0, and oh, look, it is. So that is also an H. So the 0 vector is in there. So this set we're defining as H, it's not R squared, but it's basically the same as R squared. It's kind of like taking points in 3 dimensions and just remove the height. That's it. Okay, let's consider this special subspace. Consider the 0 subspace, where it consists of only the 0 vector. Let's show that this is a subspace. Well, take any 2 vectors in this space. Well, there's only 2 vectors, right? 0 plus 0. Is 0 plus 0 in the vector space? Well, yes, because the result is 0. Okay. Again, this is a space made up of exactly 1 element. Well, if you take that element and add it to itself, you're going to get itself again. Great. Take that element and multiply by any real number, and yep, you're still going to get 0. So it's closed under scale multiplication. Is the 0 vector in there? Of course it is, because it's the only element. So it is possible to have a 0 or to have a subspace that only has 1 element. We just have to make sure that that 1 element is the 0 vector. Okay. Consider this special subspace. Let's consider any 2 vectors v1 and v2 in a vector space V. Okay. Now again, it's really tempting to visualize v1 and v2 to be in R squared or R cubed or whatever, and they might be, but we want to be careful about that. So because we want to make sure that we're considering any vector space, even the abstract weird ones. So we're going to define H as the span of those two vectors. So now remember what that means. It's the set of all vectors that looks like this. AV1 plus BV2. Every single vector in H looks like that. And we want to show that this is a subspace. Basically, we want to show that if you take any vectors, it doesn't even have to be two, it could be any number of vectors. Take any number of vectors in a vector space. The span of those vectors is itself a subspace, is itself a vector space. Okay, so let's take two of these two such vectors. So AV1 plus BV2. So there's one vector. I'm going to add that to CV1 plus DV2. Well, if I add these together, that's the same as A plus C times V1 plus B plus D times V2. Well, notice that the result is still, it's a coefficient times V1 plus a coefficient times V2. That is an element of our vector space, of our subspace, subset. So adding two vectors in H resulted in a new vector in H. Multiplying by coefficient would be CA times V1 plus CB, that's a D, whatever, CB times V2. Once again, hey, look, a coefficient times V1 plus a coefficient times V2. Yep, that's an H. And the last question is that zero vector. Well, if I did 0 times V1 plus 0 times V2, well, let's see. The coefficients can be anything, right? Coefficients can even be zeros, as we have here. The zero vector is in H. Okay, so for that reason, yep, the span of any two vectors, and again, it wasn't unique to two, the span of any number of vectors in a vector space results in a subspace. Okay? So if these vectors are in V, then the span of these vectors is called the subspace spanned by those vectors. Very creative naming, I know. Given any subspace H, a spanning set of H is a set of vectors such that H is the span of those. So basically, if you've got any subspace H, it would be nice, and you won't always be able to find it, but it would be nice to be able to find a set of vectors so that the span of those vectors defines H. And a real simple example of that, consider Pn as a subspace of F. This set, 1t, t squared up to tn, is a spanning set of Pn. Think about it. Didn't we define Pn as a naught plus a1t plus a2t squared plus dot 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 plus an tn? Well, look at that. Isn't that just a coefficient times 1 plus a coefficient times t plus a coefficient times t squared all the way up to a coefficient times t to the n? That is, by definition, a linear combination of 1t, t squared up through tn. Okay, so consider this set of vectors. A and B are real. Let's show that this is a subspace of R4. Now, we could go through the whole process, or we could just observe that that vector that's being defined there is the same as the vector a negative 1, 1, 0. Oh, I'm sorry. A negative a 0. That's what I meant to do. Plus negative 3b, b 0b. Right, so every vector in this set looks like this. And we can go even further. This would be a times the vector 1, negative 1, 1, 0. Plus b times the vector negative 3, 1, 0, 1. In other words, H is the span of those two vectors. 1, negative 1, 1, 0, and negative 3, 1, 0, 1. Every single vector in H is a linear combination of those two vectors. So H is the span of these two vectors. And let's see if it's if the subset is the span of vectors, then it is a subspace. There we go. Cool. So just showing that it's the span of vectors is enough to show that it is a subspace, because we've already proven that spanning two vectors results in a subspace. All right, there we go. That is the end of the lesson. Thank you very much for watching.